Okay, so several of you have asked about the right-hand rule, and there are three applications of the right-hand rule. I'm going to show you how I've described it in the extra practice, and then I'll show you how I sometimes describe it, and that might come up in some of the videos. But really, they're the same. It's just sort of how I talk about it. So the three applications include these three equations. We have the F equals QVB, and then also there's a sine theta term. Well, I'm going to get rid of that x right there, although I talk about that x in terms of the cross product in one of the videos, the right-hand rule extra practice video. You don't need to worry about cross products. We're not going to do that. I was just trying to explain to you, sort of where this comes from. The second equation is F equals ILB, and usually there's a sine theta term here as well. And then the third is this B equals mu naught I over 2 pi r. That's the magnetic field due to a long straight wire. The first two of these applications are really, really similar. In fact, they're basically the same. And then the third application is what we usually call the curl rule. So first of all, when I'm using the right-hand rule, I'm going to use my right hand only. Remember, you keep that test charge in your back pocket. You're also going to keep your right hand in your back pocket. That way, if you ever need it for your right-hand rule, then you'll have it. It's right here. So we use our right hand because when we situate our fingers like this, our fingers are all orthogonal to one another. That is, they're all 90 degrees to one another. I have a 90-degree angle here, I have a 90-degree angle here, and I have a 90-degree angle between my thumb and my middle finger. They're like the XYZ axes. They're right-hand. We actually call our coordinate system a right-handed coordinate system because of the way that the axes are oriented to one another. So anyway, I'm going to let my index finger be V. So this will be my index finger. I'm going to let my magnetic field be the middle finger. So this will be my middle finger. And then my thumb is going to be the force. Listen, if you want to write V on your index finger, B on your middle finger, and F on your thumb, even for the exam, like I'll allow that. But I think that after you practice with it, that you won't really, it'll become like second nature to you. I want to say too that the right-hand rule might seem, well, why are we doing the right-hand rule? I think you'll probably never see the right-hand rule again, except for maybe on the MCAT. But it's an important thing because it helps you to think in three dimensions. And that's what I really like about this chapter, because more than any other chapter, we're now beginning to think spatially in three different dimensions. And that's just not a skill that many people have. So let's do an example. Let's say that I have a positive charge traveling in this direction with a certain velocity. And it's going through a magnetic field that is in this direction. So my magnetic field is pointed upwards. And I want to know what is the force that's acting on this particle. I let my finger go in the direction of V. Now, I don't know how to orient my hand, but I know that my finger has to be in the direction of the velocity. And then I'm going to orient my hand so that my middle finger is pointing in the direction of B. And then I look at my thumb is pointing out of the page. So the force that's acting on this particle is going to be out of the page. So this particle is going to come into this magnetic field and it's going to come out towards you. Let's try another one. I'm just going to change the magnetic field now. Instead of going up as it was, I'm going to have this particle come into a region of space where the magnetic field is into the page. Remember your symbols for the plus and minus Z. So for plus Z, which is out of the page, it looks like an arrow that's coming towards you. That's just like the tip of the arrow. Often, we'll draw a circle around this. Or sometimes we don't. We'll just use dots. The negative Z direction is like an arrow going away from you, going into the page. And we draw it like the fletching of an arrow if we see it going away from us. So this is going into the page. This is in the minus Z direction. You should be able to draw or recognize the three different, or the plus and minus Z by either into the page, out of the page. Into the page is negative Z, out of the page is positive Z. You should be able to recognize it by the symbols or symbols like this. So here, V I don't know how to orient my middle finger yet until I know the magnetic field, but it's going into the page. And then my thumb gives the direction of the force. So this particle feels a force that is upward. So my force is going to be like this. That means that as this particle travels, it is going to travel in a path that goes like that. This is a mass spectrometer, and part of your videos talked about how a mass spectrometer works, that you measure that radius to determine what is the mass to charge ratio of that particle. Now let's look at the second application. Oh no, let me say, by the way, that I talk about in the book, or in the videos, I talk about folding your fingers towards the magnetic field. And so this is a slightly different application. It's still the same answer, but I talk about letting your fingers go in the direction of V, and then they fold towards the magnetic field, and then your thumb gives the direction of the force. But see, that's exactly the same as having my hand like this, index finger in the direction of V. My middle finger should be into the page now, and then my thumb gives the direction of the force. Let's do this one. The second application is ILB, where I have a current going in a certain direction. Let's say that there is a magnetic field that is into the page. That's my magnetic field, and then I want to figure out the force. This one is exactly the same as the first application. In fact, this problem was the same answer as this problem. That is, my force is going to be acting upwards. Let me show you. Finger in the direction of I. My magnetic field goes into the page, so I know I have to orient my hand in this direction. And then my thumb gives the direction of the force, which is going to be upward. Let's try another one. So let's say that I is like this. That's I. And then let's say that the magnetic field is like this, to the right. Thumb or index finger in the direction of I. Then I have to orient my middle finger so that it points to the right in the same direction as the magnetic field. And now my thumb gives the direction of the force. So my force is going to be into the page. This is exactly the same. Now, just a little aside for those of you who remember that current is a scalar quantity, and if you're familiar with the cross product, then you recognize that, hey, current isn't a vector, so you can't take the cross product of a scalar quantity. However, L is a vector. L is in the same direction as I. So when I talk about the direction of the current, I'm really talking about the direction of the wire. Don't let that bother you. It doesn't really matter for our discussion, but we'll just always assume the direction of the current, and we'll assume it to be like a vector quantity, even though it's really not. All right, now next is u naught I over 2 pi r. And on this one's a little bit different. Imagine I have a current that's traveling in this direction. A current carrying wire generates a magnetic field. The magnetic field of a wire with a current in it is equal to mu naught I over 2 pi r, where r is just the distance from the wire. So there is a magnetic field at that point, and at every other point away from that wire. And I want to figure out what is the direction of that magnetic field. So I'm going to let my thumb go in the direction of the current, and then my fingers will wrap around to give the direction of the magnetic field. So thumb in the direction of the current, they go into the board on this side, and they go out of the board on that side. So my magnetic field, if you imagine this is the wire, the current's going up, I let my thumb go in the direction of the current, and it folds around like this. And so that magnetic field is going to go into the page on this side and out of the page on that side. I'm going to erase this. Let's do one other, where now I'm going to have a wire that's in the z direction. So this is a current that is coming out of the page, and I want to know what is the direction of the magnetic field. So my wire is coming out in this direction. my fingers fold around like this. So my magnetic field is, what's that, counterclockwise. My magnetic field is counterclockwise. Thumb goes in the direction that my fingers wrap around. Now recognize that if this instead was into the page, then it would just switch directions. It would then be not counterclockwise, but clockwise. The magnetic field generated by that wire going into the page. All right, we'll do some more problems on the screen where I'll look at some old test questions. But you're going to have a lot of right-hand rule stuff, and some of them will be more complicated than this, but we'll do those looking at some of the old test questions. Oh, by the way, I just want to say that I really miss all of you. So I'm not really cut out for online teaching because I think that I just like students too much to really just talk to you over email and video, and that's just not really the same. So I'm not going to see you again for the rest of the semester, but I just want you to know that I don't like that, and but it's going to be okay. That we're going to continue doing what we're doing. We're going to make you the best physicists that we can, so that you'll be ready for all those various things that you're going to go out.